model, which is what we're covering in section 8.6. So the binomial probability model is one of many dozens of different probability models that are used in various fields to analyze various types of data. Each of these probability models has a set of assumptions associated with it, which determine whether you can use that particular probability model with a set of data that you have. So we will look at these set of assumptions for the binomial probability model. So in graduate schools usually, or sometimes at senior level in undergraduate levels, you are given some data, or you're collected some data that you want to analyze. How do you determine which types of probability model you should use with your data? So the assumptions are what you look at. The other thing is that with respect to the binomial probability model itself, it came out of a type of experiment that was called the Bernoulli experiment. Bernoulli experiment, which is associated with the work that Bernoulli brothers did in various areas of science and mathematics and engineering, it's a type of an experiment that has, regardless of how many outcomes you have, all the outcomes are divided into either a success event or a failure event. The success event is the event that you're looking for. For example, suppose you are an inspector who was hired by an independent agency to look at the number of defective CD-ROMs that are coming out of a CD-ROM factory. And you're looking for the defective ones, not the good ones. So as you randomly sample the assembly lines for these CD-ROMs, if you're looking for a defective CD-ROM, and if that's what you're finding, if you find a defective CD-ROM, then that is considered a success event. So the main point I'm trying to address here is that success is not necessarily associated with finding or coming up with a good or desirable outcome. It may or may not be something desirable, but it's something that you're looking for. And if you find something that you're looking for, that event, even if it's a defective object or item, it is considered a successful event. So having said that, let's go forward with our detailed discussion of the binomial probability model. So first off, I want to write down what I said a few seconds ago, which is that a Bernoulli experiment has two types of outcomes. Right? It could be 300 different 300 outcomes, but as far as the type of the outcome we're concerned, right? The type of outcomes can be either a success or a failure. For example, you can flip a coin 500 times, right? So, but if you are looking for heads, then every time the coin comes up a head, that is considered a success event. And when that is not happening, when you're getting a tail coming up, that event is considered a failure event. Okay, so examples of these. What are some of the examples of binomial experiments? These can be vaccine trials, right? If a vaccine works, then it's considered a success event, and if it doesn't, it's considered a failure event. Assembly line quality control. That's another type of data with which you can use this this probability model. Tossing a coin, like I said a minute ago, etc. So, as I said earlier, the determining factor as to when you can use a particular probability model relies on the assumptions for that probability model. Very, very important. So let's see what those assumptions are for the binomial probability model. First of all, the total number of experimental outcomes, it has to be fixed. Going back to the CD-ROM example, right? Suppose you're an inspector inspecting an assembly line for a factory that manufactures CD-ROMs. Now, from the outset, you have to establish how many CDs you're going to select at random. You can't just approach the assembly line and pick 100, sometimes maybe 20, sometimes maybe 80. No. The number of CDs that you're going to pick to inspect has to be fixed and known from the outset, and you cannot change that. So if you're going to inspect 50, you have to establish that number, and you have to stick with that 50 from the outset. And so this number one assumption addresses that part of the binomial probability model. So the total number of experimental units, in the formula that's considered lowercase n, so I'm going to give it that name, is fixed and does not change. If you change that, then you have violated that assumption of the binomial probability model. Number two, the outcomes, each outcome is independent of the other outcomes. So the outcomes are independent of each other. And the probability, we just talked about success and failure events. The probability of success event is fixed. The probability of a failure event is fixed as well. So we've talked about complementary events in the past, right? So successful and failure events, these are complementary events. So if you know the probability of one, you know the probability of the other. Suppose we know that the probability of success is 0.25. Then the probability of failure, it would be 0.75, right? Just 1 minus 0.25 gives us the probability of failure. Now, probability of success, I should mention the variable that is associated with this, and that is p, lowercase p. So that's the probability of success. Probability of success. The probability of failure, that is the letter q, which is equal to 1 minus p in the formula. Okay, so having discussed this, then let's write down the formula for a probability, for a binomial probability model. And I'll put that on the next page. So this is K. I'll use letters that your textbook uses. So if you, when you compare these two together, the textbook and this, it'll match. So this is the formula for calculating binomial probability. And we've kind of defined these variables, but let's do it again, just underneath the formula. So the n is the total number of experimental outcomes and that is fixed. K is the number of success events so if you're looking for 5 defective CD-ROMs, if you find that, so that is considered the K value, K equals 5. And P is the probability of a success event. And Q, which is equal to 1 minus P, 1 minus P is the probability of a failure event. This piece, this is not n divided by k, this is n choose k. This is the combination calculation we learned in chapter 5, 8.5. So I should write it here. It's called, the way we read this is quotation marks, n choose k. That's how we read that. N choose k, not n divided by k. There's no division going on here. N choose k is the same thing as the combination of events, which was the topic of section 8.5. Okay. So you know how to calculate this, right? We've talked about how to calculate the combination of events in section 8.5. There is a formula is associated with it, but we've talked about how to use that calculator button on your calculators to calculate this. So either way will work. And if you have questions about this, please come to me or post your questions on the discussion board so I can answer that if you have questions about this piece. But this is equal to n factorial divided by k factorial times n minus k factorial. So that just calculates that, but we've talked about this in section 8.5. You should be able to use the calculator button to come up with that value. You shouldn't have to use the formula at all. But in case you're interested or want to, or if you have questions on it, just let me know. The other thing is that earlier I said that there are dozens and dozens of probability models that are associated with various types of data. Now, each of those probability models has an expected value formula associated with it, which is different than the expected value formula for other probability models. So for the binomial probability model, the expected value formula is very simple one. It is, so expected value E is equal to n times p. So we know the number of experimental outcomes. We times we multiply that by the probability value, probability of success, and we get the expected value. Okay, so now that we've introduced this binomial probability model formula, let's see some examples. So suppose that we have a study that has found that 45% of workers like their jobs. Suppose 7 workers are randomly selected, assuming that the data has binomial distribution. Here's the first question, or part A. What is the probability that all 7 like their jobs? Okay, so notice now in this formula we have to be able to identify what variable is associated with which one of these quantities we are given. So let me write down the original probability model formula. Right, that's our formula. So a study found that 45% of the workers like their jobs. And what is it that we're looking for? The probability that all 7 like their jobs. So K in this case is the type of event we're looking for. And that event is those who like their jobs. And K would be 7 in this case, exactly 7. Right? So K is equal to 7. So what is the value of n? Notice that 7 workers were randomly selected, so that is n. And 45% of the workers traditionally reported that they liked their jobs. So P, that's the probability of success, right? Probability of someone liking their job. So, and that is 0.45. We have to convert this to decimal form. So assuming that the data has binomial distribution, that means we assume that all the assumptions for the binomial probability model have been fulfilled or satisfied, then what is the probability that all 7 like their jobs? So then the question for us is, what is the probability of k equals 7? Okay, so let's plug in. N is 7. K is 7 also. P is 0.45. Raise that to k power, which is 7, times 1 minus Q is 1 minus P, or 1 minus 0.45, raised to 7 minus 7 power, or N minus K. N is 7, K is 7 in this case. 7 minus 7 would be 0, right? Okay, so now we can calculate this by using, here's what I showed you in section 8.5. We can do that here, hopefully. So I want to, 7 choose 7, we would expect this to be 1, right? How many ways we can choose 7 out of 7 such that order does not matter? There's only one way to do that. So, but let's calculate it. So we have 7. So 7 on this calculator, PRB, NCR, right? That's the combination, NCR. I'm going to hit enter to pick that, and then 7 choose 7, and then we say, I hit the equal button, and now we have 1. So 7, so this quantity is 1. 0.45 to 7th power is 0.003737, and any number raised to 0 power, this is 0, 1, so minus 0.55 to 0 power is 1. Okay, so multiplying all of that, we get the same number, right? 0.003737, like that. So I have carried this over to 1, 2, 3, 4, 5, 6 decimal places. Okay, so this is 6 decimal places. So if I wanted to round this to 4 decimal places, then this would be 0037, right? And if this was 5 something, I would round this 7 to 8. For part B of the same question, this is going to be a little bit, I need more space for this, so let me go to the next page for that. Okay, so for part B, we're asked, what is the probability that at least, you guys have seen this before, right? At least, it's very important, at least 2 like their jobs. Okay, so let's get our heads around this question, because this makes this part B, very, very different than the question in part A. Part A, see, in part A, we were asked, what is the probability that all 7 like their jobs? This is what is called exact probability. Exact probabilities ask you for the probability of a single outcome. Suppose if I said, what's the probability that 2 didn't like their jobs? Then that would be an exact probability. What's the probability that 5 liked their jobs? That would be another exact probability, right? But if I say something like probability that no more than 2, at least 5, at least 2, those phrases turn that type of probability calculation, they change the exact probability to what we call an interval probability. So at least 2, this is an interval probability calculation. And let's translate this to a symbolic form. So this would be probability that k at least 2, not equal to, at least 2. So greater than or equal to 2. Right? Greater than or equal to 2. So now, because binomial probability distribution is a discrete probability distribution, it has discrete outcomes. So in order to calculate this probability, we have to add individual probabilities. This is the same thing for all discrete probability distributions. Those of you who are taking Econ 261 or have already taken it, you're pretty familiar with what I'm talking about if you've already taken Econ 261. With discrete probability models, of which the binomial probability is 1, we have to add individual probabilities. So probability that k is equal to greater than 2 means that probability that k can be equal to 2 plus, so we're adding, right? Probability that k can be equal to 3 plus probability that k equal to 4 plus probability that k can be equal to 5 plus probability that k can be equal to 6 and plus probability that k can be equal to 7. That's what we need to do with all probability for all interval probability models. We always have more than one calculation. With exact probability model or exact probability calculation, you always have one calculation. With interval probabilities, we always have more than one. So in this case, we have 1, 2, 3, 4, 5, 6 calculations to do. Now this, applying the binomial probability model 6 times, it can be time consuming. The question is, can there be a shortcut? So let me write that down. So could there be a shortcut to all these calculations? And the answer is yes. So the shortcut calculation for all of this is that this is what we want, right? So we find the complement of this, which is not what we want. But if we find what we want, and we have to do fewer calculations for that, and subtract it from 1, we get what we want with fewer calculations. So using complementary events, we can write probability of k greater than or equal to 2 plus probability that k is less than 2, right? This is not what we want this, but this is the complement of that. Plus that must be equal to 1. We know that. We know that from several weeks ago or several sections ago that any event plus its complementary event, the probability of those, probability of any event plus probability of the complement of that event must be equal to 1. So then we can say probability of k greater than or equal to 2, which is what we want, right? This is what we want. That is equal to, let's do the algebra on this, 1 minus probability of k less than 2. So now let's find this. So we have 1 minus probability k being less than 2. What could it be? It could be that we surveyed these 7 individuals and 0, none of them liked their jobs, right? So probability that k equals 0 is part of this, plus probability that only 1 out of the 7 liked their job. So here, anything you have in in the middle of this bracket is the complement of what we want. We find the complement of what we want and subtract it from 1, and we find the probability of what we're looking for. What is the advantage of this? I mean, it's clearly that we have to do a lot less calculation here, right? Above, we had to do 6 calculations. Here, we can do only 2 and add those 2, subtract from 1, and we have the same value. So let's do that. So this is just a shortcut. This method of subtracting a probability from 1 is just a shortcut. Okay, so let's do that. So we have probability of k greater than or equal to 2 is equal to 1 minus. I'm going to write the probability model for this piece first. So we have 7 choose 0 times 0.45 to 0 power times 0.55, which is 1 minus that, right? To what power? Can you think of what power this should be? It's n minus k. So 7 minus 0, 7, plus the next one. Now this one. 7 choose 1, right? K is 1. 7 choose 1 times 0.45 to first power times 0.55, and then this power, what should it be? Can you say it? 7 minus 1, 6, right? And we can close the bracket. So instead of 6 calculations, we have only 2, and then we can subtract from 1. Okay, so let's write this out. So we have probability of k greater than or equal to 2 is equal to 1 minus. 7 choose 0, it's 1. You can calculate this. Oops. The lens just dropped. So let me fix this. So okay, we're back. Okay, so 7 choose 0 is 1. Can we show it? Sure. So we have 7, the PRB button. Use the arrow key to scroll over to NCR, which is the combination. Hit enter to pick it, and then enter 0. And then press enter. 7 choose 0 is 1. Okay, so that's 7 choose 0, 1. Anything to 0 power is also 1. 0.55 to 7th power, if we calculate that, we get 0.015224. Notice in the middle of my calculations, I'll keep 5, 6 decimal places in the middle of my calculations. At the end, you can always round things up. But in the middle of calculations, don't round too early or you'll end up with a final answer that is way off. So in the middle of your calculations, keep at least 5 or 6 decimal places. That way your final answer will be very, very close to the actual value. Okay, so now plus 7 choose 1, it's going to be 7, because in how many ways we can choose 1 out of 7? 7 ways, 7 different ways, right? So let's calculate it. We're going to calculate this quantity. So 7, the PRB button, use the arrow key to go to NCR, hit enter, and then enter 1, 7 choose 1, which is what we have. Hit enter, we get 7. So 7 times 0.45 times 0.55 to 6th power This caret is the power button to 6th power, and we get that number, right? 0.0276806. So I'm going to round that 0 to 1. Okay, so times 0.02768, and it barely fit over there. Okay, so then we have probability that k is greater than or equal to 2 equals 1 minus, then multiply all of that, we get 0.015224 plus 0.087192. So that is equal to 1 minus 0.102416 equals 0.8976, and that's the final answer. So that's the probability that we surveyed these 7, and at least 2 people said that they like their jobs. Okay. I trust that you have questions. Please don't forget to ask those questions either directly or type them right underneath the video on the discussion board. So now part C of the same problem, we're asked to calculate what is the probability that no more than 4 like their jobs, or like their jobs. Okay. No more than 4, we have to translate this into symbolic form. Oops. Sorry, I was way off the screen. Okay. That's better. What is the probability that no more than 4 like their jobs? So translating that into symbolic form, we have k less than or equal to 4, right? Okay, so that's the translation of that. How many, because this is a discrete probability model, the binomial is, so how many calculations would this be? Well, the calculations would be probability of k equals to anything equal to 4 or less than 4, right? It could be 0, that is nobody liked their jobs out of the 7, plus probability of k equals 1, plus probability of k equals 2, plus probability of k equals 3, plus probability of k equals 4. Right? That's all because this is an interval probability. Remember, with interval probabilities, we always have more than one calculation. Okay, so we have 1, 2, 3, 4, 5 calculations. Okay, can we have a shortcut for this? Let's see. So we had so we can have a shortcut, right? So the question is, could we use a shortcut for these 5 calculations? The answer is yes. Yes, there is. So what would that shortcut be? Well, we know that we can rewrite this in terms of its complement, right? So we can say probability of k less than or equal to 4 plus probability of k, let's write the complement of this, greater than 4 would have to be equal to 1. Okay, then probability of k less than or equal to 4 can be written as 1 minus probability of k greater than 4. I'm just doing the algebra on this. And so this would be 1 minus probability of k greater than 4 would be, let's see how many events do we have. So that would be 5, right? Greater than 4, not equal to 4. Equal to 4 is part of what we want. So greater than 4 would be probability of k equals 5 plus probability of k equals 6 plus probability of k equals 7, right? So we only have 3 calculations to do as opposed to 5. Again, using the shortcut, we had 5, we had to do 5, but using the shortcut, we only have to do 3 calculations. By the way, remember this one? This piece, probability that k is equal to 7, we already calculated this in part A. Let me move this up. We already calculated this piece in part A. So we really have to do 2 calculations. So let's do that. So I'm going to start from here. So probability that k is less than or equal to 4 is equal to 1 minus. I'm going to apply the binomial probability model to this one. 7, choose 5, right? Times 0.45 to 5th power, which is the power of the success is equal to the number of success, times 0.55, 7 minus 5, second power, or squared. Let's write the binomial probability model for this one, k equals 6. So that would be 7 choose 6 times 0.545 to 6th power, right? That's the number of successes for this one. So it becomes the power of the probability of success times 0.55 to what power? 7 minus 6 is 1. And of course, plus whatever we found from part A for k equals 7. And that was, I'll just bring this back for 1 second. This is the slide for part A, 0.003737, right? So we have add 0.003737, and then we can close the bracket. And once again, let me make sure that everyone knows this is from part A. Okay, so all we have to do is calculate these different pieces and plug them into there and do the algebra on this. So we have probability of k less than or equal to 4 is equal to 1 minus, so 7 choose 5. Let's calculate this piece, 7 choose 5. 7, PRB button, use the arrow key to go to NCR, hit enter to pick it, and then enter 5, like that, and hit enter again, you have 21. So 7 choose 5 is 21, times 0.45 to 5th power is 0.0184528. 0.55 squared is 0.3025 plus, I'm going to run out of space, so let me put this underneath it. 7 choose 6. Let's calculate that. Right, we're going to calculate this one. So like that. So 7 PRB, scroll over to that, NCR, 7, choose, enter 6, and hit enter, you get 7. So 7 times 0.45 to 6th power, we have 0.008338 times 0.55 to first power is 0.55, right? Plus the last piece, which is 0.003737, which we had from part A. So adding all of this, so what do we get when we, so we have probability of k less than or equal to 4, 1 minus, multiply all of that, we get 0.11722, plus, please double check my numbers, multiply all of this, you should get 0.03196 plus, adding this last piece, which we got from part A, 0.003737. So that'll be 1 minus 0.1529167. Again, notice that in the middle of my calculations, I keep so many decimal places. And then at the very end, I'm going to round it to 0.847. Okay. So now, let's take a look at another example. So we have this information about Insurance Bureau that estimates that 15% of auto theft claims involve fraud. Suppose 12 auto theft claims are randomly selected. Involve fraud. Okay, so we have this Insurance Bureau that estimates that 15% of auto theft claims involve fraud. Suppose 12 auto theft claims are randomly selected. Up to this point, you should have a pretty good idea about at least 2 of the variables in the binomial probability model. For example, what is this 15%? It's about those auto theft claims that pour into this insurance company because of fraud. And what are we looking for? We're looking for determine the probability that none of the claims involve fraud. So that 15% is P for us, because it's the probability of what we're looking for. Claims that involve fraud may or may not involve fraud. So 0.15. And then we picked 12 auto theft claims at random, right? So this n is equal to 12, and it's fixed. We can't change that. It's going to remain 12. And then, knowing that the data has binomial probability distribution, we are told that, so that means all the assumptions have been satisfied. Determine the probability that none of the claims involve fraud. Well, that none of the claims, that means k equals 0, right? And by the way, what is q at this point? You guessed it. If you said q is equal to 1 minus 0.15 or 0.85, you are correct. Because if you know p, you know the value of q. Okay, so let's write down the calculation. We would have probability of k equals 0. Is equal to, we have total 12, and we want to see if what's the probability that none of these 12 involve fraud. And probability of P is 0.15. To what power? To the power of the number of successes we have. 0 times 0.85 to what power? To power n minus k. 12 minus 0 is 12. Okay, so then if we expand this, 12 choose 0 is 1, right? We can quickly calculate that. So 12, PRB, use your arrow keys to scroll to NCR and hit enter. So 12 choose 0 is 1. And then anything to 0 power is also 1. 0.85 to 12 power is 0.142242. So multiplying these, we have 0.1422, and this is the answer rounded to 4 decimal places. A good idea would be at this time, because you've already seen one example, would be once I write down each of these examples, pause the video, run your own calculations, and then come back to the video. So for part B, we want to determine the probability that 2 claims involve fraud. Okay. So this is, what do you think? Is this the exact probability or interval probability? Think about it. See, the 2 claims is just, it doesn't say more than 2 or less than 2 or no more than 2 or at least 2. So this is exact probability. So we only have to calculate this once, or one calculation. That's all we have to do. Okay, so we have probability that k equals 2 equals 12 choose 2, right? 12 choose 2 times 0.15, which is p, to what power? To the number of successes. 2 times 0.85 to what power? 12 minus 2, which is 10. Okay, so 12 choose 2. Let's calculate that. We want to calculate 12, choose 2, so enter 12. Then the PRB button. Use the arrow keys to go to and choose R. Hit enter to select it, and then enter 2. This 2, and then hit enter again, 66. So 12 choose 2 is 66. Times 0.15 to second power is 0.0225. 0.85 to 10th power is 0.19687. Equals, and multiply all of this, and you should get 0.292. And please double check my numbers. Okay, so for part C, the question wants us to calculate determine that at least that phrase, at least again. At least one of the claims involves fraud. Okay, so let's translate that into symbolic form, right? How do we write that out in symbolic form? So probability that at least one, so K is greater than or equal to 1, right? That's at least. K greater than or equal to 1, and K being the number of successes. Well, we have, in this case, there were n was equal to 12. So 12 auto theft claims filed by customers were chosen at random out of thousands or tens of thousands. We don't know, but these 12 were chosen at random. So this, because this is an interval probability, it involves more than one calculation. But how many calculations? Well, K equals 1 being one of those calculations. Then probability that 2 involve fraud, plus probability of K equals 3, plus probability of K equals 4, plus probability of K equals 5, plus probability of K equals 6, plus probability of K equals 7, right? 7 people said that, or 7 of the claims involve fraud, the probability of that, and so on. How far should we go? If you answer 12, you are right? That's the number of, maximum number of our sample, or the sample size, n equals 12. So probability of K equals 11, plus probability of K equals 12. How many calculations is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all 12, right? Too many calculations. So could there be a shortcut? Remember, if this was just 2 calculations, I would not be looking for shortcuts, right? Even 3, I might just do it, the 3. But definitely 1 or 2 calculations, I would not look for any shortcuts. But since I have 12, let's see if could there be a shortcut to all of these calculations. And the answer is, of course, yes, there is. So let's write down the complement of this. So we can say that probability of K greater than or equal to 1 can be written, probability of K greater than or equal to 1 plus probability of, write the complement of this, K less than 1, right? This is the complement of that. This plus its complement should be equal to 1. The probability of any event in the sample space plus probability of the complement of that event in the sample space should be equal to 1. This is a very useful formula. So let's calculate then probability that k is greater than or equal to 1, which is what we want, is equal to 1 minus all of this moved to the other side. Probability of k less than 1, right? So let's see how many calculations is that. This is 1 minus probability that k equals 0. Just one calculation, right? This is just one calculation. K less than 1, that means k equals 0, which means they out of the 12, none of the claims involve fraud. That would be that. But remember, we calculated this already, right? This we've already calculated from part. So already calculated in part A. So we can write it. So probability of k being greater than or equal to 1 is equal to 1 minus, that number was 0.1422, and so we have 0.8578. So we didn't even have to use our calculator for this, right? Using these various things, the shortcut, and remembering that we already calculated this piece for part A, we didn't even need to use our calculator for this. So very quickly we were able to obtain the answer. So for part D, this is the last part. It says how many claims do we expect to be fraudulent, right? Remember what this phrase means in this course? Remember what that means? That means the expected value, right? It's the same thing as the expected value. And it is equal to, for the binomial probability model, it's equal to this formula. E is equal to n times p. Now, for the benefit of those of you who will be taking the Econ 261, if you have other probability models that are discussed in that course, the expected value of those probability models will be different than the one we're using for the binomial probability model. Just be aware of that. Because in mathematics, calculating the mean or average of values, it's always the same. You add up all the values for which you're calculating the average, and then divide by how many values you've added, and you get the average. But in statistics and probability, the expected value, depending on the probability model that you're calculating, will be different. So for the gamma distribution, you'll have a different formula for calculating the expected value. For alpha distribution, you have different. For a uniform distribution, you have a different formula, and so on. And this is for those of you who will be taking Econ 261. Okay, so let's plug in for these values. For n, we know it's 12. P, we know it was 15%, right, or 0.15. So multiplying, we get 1.8. So every time I talk about this where people are present in the classroom, I always get a question, well, how can you get 1.8 claims involving fraud? Should we round this up to 2 at least? I say no. With expected value, quite often you get decimal values like this, where it's not a whole number. It's fine. We're not going to round this up. You just leave the answer as is, as the expected value. Okay, so this wraps up section 8.6, which is the last section in this we had to cover in this course. Please post your questions on the discussion board right underneath the video. And I hope that you're staying safe and well, you and all of your families. I hope the best for you. And then I wish you well on the final exam. Have a very good day.